So dear students, now we are going to see the next metal forming process, that is the part of drawing, that is nothing but the tube drawing process. We have seen the wire drawing. Okay. So the tube drawing or pipe drawing we are going to see. So the same process as like the wire drawing, but here we are going to produce the tube. Okay, so which is already drawn by some other process. Just we are going to do the sizing of this tube in this operation, that is the tube drawing process or pipe drawing process. So see, this process is basically same as that wire drawing process, only the thing is that the die which we are going to use in this tube drawing is larger in size than the die in the wire drawing operation. Okay, so here I will draw the diagram for tube drawing operation. So same die, just I want to, or directly I can have the huge. So here is the pipe of thickness and here we are going to have the mandrel for the purpose. Say this is initial thickness of the pipe and this is the final thickness of the pipe. This is outer diameter of the pipe and this is the inner diameter of the pipe. Okay, and this is of course the die, larger in size. Okay, so see, this is the mandrel we are using for the purpose of the having the sizing of the thickness of the pipe. Okay, if you are using the cylindrical mandrel, then we can do only the sizing of the inside surface of this tube. To reduce or to change the thickness of this pipe, we can use the conical mandrel. Okay, so suppose if this is the diangle alpha, 2 alpha full diangle, and this is the conical angle, say beta, and here what is the thing, here say the coefficient of friction between the outer surface of the tube and the die is say mu1, and there is a coefficient of friction between the outer surface of the mandrel and inside surface of the tube, that is mu2. Okay, so this is the thing here. So here in tube drawing process we are not going to make the tube, but we are going to sizing, we are going to have the sizing of the produced tube by some another operation. It is produced and we are doing the sizing here. So basically we are having, there are three types of these tube drawing operation. One is, we can call it as the tube sinking, another is the plug drawing, and last one is the movable mandrel. Okay, so here actually in tube sinking we are not going to use any kind of this mandrel or plug inside this tube surface. So what happened, that is there is no support for the inside surface of the tube, so dimensional accuracy is quite less in case of the tube sinking. But if you look at the plug drawing operation, so this mandrel which we are using here, it may be a straight cylindrical mandrel or it may be the conical mandrel. Okay, and it may be the stationary or floating. So in the, if you look at the types, we are having tube sinking. Tube sinking mein kya hai, there is no any mandrel inside the tube. Okay, so what happened, because of that, in the inner surface having no any support, so the dimensionally you are getting not okay part. Okay, या फिर इसकी डायमेंशनल एक्यूरेसी इतनी अच्छी नहीं है. Okay, then the second we are having the plug is nothing but mandrel only, plug drawing. Okay, so here this plug may be cylindrical Plug or mandrel is same, cylindrical or conical. Cylindrical or conical. Only the difference is that if it is a cylindrical one, so what happened? So there will not be any change in the inner dimension, just we are going to have the sizing operation. Okay, so here for the cylindrical mandrel, so beta value will be 0. Okay, and there is, cylindrical mandrel beta value is equal to 0. For conical mandrel, some beta value is there. Okay, this is the cone angle, isn't it, for the conical mandrel. And if you talk about generally for the movable mandrel, so movable mandrel, it is again taken as the straight cylindrical mandrel. Straight cylindrical mandrel. Okay, if you look at in this plug drawing, or it is in the stationary or moving, stationary or floating. Again here we are having, it may be the stationary and moving, or it is also known as the floating. Okay, so the friction will be maximum in stationary mandrel. Friction is more compared to the moving mandrel. Here friction is less. Okay, and as there is no any change in the internal dimensions of the this tube, okay, only we are going to have the change. See here, only we are getting the change in the thickness. Okay, so there are some amount of changes definitely there, just when we are inserting the mandrel inside it before the drawing operation. So that is only the deformation we get here, but only the thickness in this thickness. So that's why please remember the tube drawing operation is treated as the operation with the plane strain condition. Okay, so here the plane strain condition is valid for the tube drawing operation. Please remember. So in rolling operation we have seen the plane strain condition valid. Now in tube drawing operation the plane strain condition is valid. Please remember it. So of course, if you want to determine the load or the force in the tube drawing operation, so again there are the two conditions. One is with the ideal deformation, and the second one is by considering the friction and redundant work. Redundant work you know very well, that is loss in the work, it is inhomogeneous work. Okay, so of course the drawing stress, now we are interested to find out the drawing stress in case of, say, it is ideal deformation. So we know that what is sigma d? Sigma d is equal to sigma y. Now here plane strain condition, so sigma y will be replaced by sigma y dash, isn't it? ln of what? H original divided by H final. See, here is the thickness H original and H final. So here sigma y will be replaced by 2 by root 3 for plane strain condition times the nominal stress or yield strength of the material into ln of H original by H final. This is your drawing stress in the tube drawing operation. Okay, now what is the force? So force is what? The stress into area. Area kaun sa? This final area final, which is equal to sigma d into pi by 4 d outer square minus d inner square. It is a pipe, no? So this is the force we can calculate, isn't it? Now anybody asks you to find out the maximum possible reduction in this tube drawing process, then how to find out? We know that for maximum possible reduction, what is the condition? The whatever the drawing stress is equal to what? The yield strength of the material. If we equate these two, let us equate, what we will get? For maximum possible reduction, now we are doing the work. For maximum possible reduction, what is the condition? Sigma d should be equal to sigma y. So here 1 is equal to, this get cancelled, sigma d and sigma y get cancels. So 1 is equal to 2 by root 3 ln of h original by h final, isn't it? Or root 3 by 2 is equal to ln of h original by h final, or e to the power root 3 by 2 is equal to h original by h final. So this is very important equation. Okay, now what to do? We want the maximum possible reduction. Then how to find the maximum possible reduction? So maximum possible reduction, you know, the maximum possible reduction is equal to what? So it is a thickness. We are not having the area, okay, because whatever the change we are getting into the thickness, isn't it? So it will be, we can write it as, in the rolling operation, what we are write, that is h original minus h final divided by h original into 100. So 1 minus h final divided by h original into 100. And what is 1 minus h final divided by h original? From here we can write reciprocal of this, 1 minus 1 upon e to the power root 3 by 2 into 100. So please calculate what is the maximum possible reduction you can get in the tube drawing operation. So if you calculate this, you will get it around 58%. Please remember, in tube drawing operation, the maximum possible reduction, by considering the plane strain condition, we are getting 58% reduction, whereas in wire drawing operation we have already calculated, we got the maximum possible reduction around 63%. Okay, so this is the first condition, and with that we have seen the drawing stress, then the force, then the maximum possible reduction. Same process as like wire drawing, we can also able to calculate the power if you know the velocity of tube drawing, so you can get it very nicely. So next thing is that is by considering the friction and redundant work. So how to calculate drawing stress? Sigma d is equal to sigma by into bracket 1 plus b divided by b into bracket 1 minus h final divided by h original to the power b. Okay, so again the same type equation where what we seen in the wire drawing, isn't it? So thing is that only here the value of b, see, it is equal to mu1 plus minus mu2 divided by tan alpha minus tan beta. Very important. So see here, now we will take the cases. Here we can use the cylindrical mandrel. Okay, here we can use the conical mandrel, which is a plug type, either stationary or floating, and the third type we are using the movable mandrel, which is generally, please remember, it is generally cylindrical in shape. Movable mandrel, cylindrical in shape. So whenever we are having the cylinder as a mandrel, the shape of the mandrel as a cylinder, so of course at that time this beta value will be 0. Please keep it in mind, beta value will be 0 when straight cylindrical mandrel we are using, as there is beta becomes 0. Okay, but when there is a conical mandrel, then we are having beta some value. Okay, then this beta having whatever the conical angle will have the value there for only conical mandrel. Please remember. And one thing, when the mandrel is stationary, stationary, of course I have already told that there will be the maximum friction. Okay, so here this mu1 and mu2, that is coefficient of friction between the die and the outer surface of tube. Mu2 is the coefficient of friction between the inner surface of die and outer surface of the mandrel. Yes, there will be the addition of these coefficient of frictions. So there will be the in case of the stationary mandrel, so you have to use here the positive sign, that is mu1 plus mu2. Okay, and if the mandrel is moving, mandrel is floating, say, because moving or floating is same, but I am talking about the cylindrical and conical mandrel, these are the things. So it will be the negative sign here. Okay, negative sign, please remember. So whenever cylindrical mandrel will be there, this beta value will be 0, only alpha is there, that alpha is what? Half the die angle. Now in that, if the mandrel is stationary, you have a maximum friction. If mandrel is floating, you are having minimum friction. That is minus sign there. Now see, the third case I am saying, in case of the movable mandrel, in case of the movement mandrel generally कैसा होता है? It will look like this. It is like a cylinder, okay, and it is movable. So here for movable mandrel generally, please remember, this beta is of course 0, but here the one thing is that this mu1 and mu2 are same. This mu1 and mu2 are same. So what the equation we are going to get here for B? So B, this beta is 0, okay, and this mu1 minus mu2 is 0. What is going to happen? So is that B is equal to 0? No, please remember, for whenever the word movable mandrel will appear in the question, they are not going to give the mu2 value. They will simply say the coefficient of friction will be this. No two values they are going to give you. Okay, so that we have to consider what? Mu1 and mu2 are same. So definitely there will be 0. So in that case, how to determine the sigma d? Isn't it? So this B value, you understand the cases. Now for the movable mandrel only, which is like this cylindrical shape, having beta is 0, then what is about this capital B? That is not going to use. Then the sigma d for such a case मतलब movable mandrel है, cylindrical है और mu1 is equal to mu2 है, then sigma d is equal to sigma y log to the base 10 1 upon h original divided by h final minus 1. This is the stress, drawing stress we can get for the tube drawing. And of course in both the cases, the force if you want to find out, then sigma d into pi by 4 जो final का diameter outer मिला है minus initial diameter of that pipe or tube, it will be the force, isn't it, times Newton. And of course power will be this force into velocity in watt. In watts you are going to get. Please remember, okay, for tube drawing operation we have seen the formulas. For the ideal case of deformation, maximum possible reduction by the plane strain condition 58%. Now as by considering the friction and redundant work, you get this formula, isn't it? And based upon whether the mandrel is cylindrical or conical, or mandrel stationary or floating, or mandrel is movable, we have seen the cases for calculation of this B, as well as special case you can have the movable mandrel. You can calculate the sigma d value like this. We will take one of the numerical on this. See what is given in the question. A pipe of annealed steel, inside diameter 50 mm and wall thickness 2.5 mm is to be reduced down to 48.7 mm and 1.75 mm. Diangle is 30 degree, mu is equal to 0.1 and draft is 3.12. What is the ratio of pipe diameter, pipe drawing force on plug and on movable mandrel? Okay. So what is given, see here, as there is no much increase in diameters, only the thickness is going to change from 2.5 millimeter to the 1.75 millimeter, isn't it? So here, see here, H original is how much? 2.5 mm, H final is 1.75 mm. Okay, the diangle is alpha is how much? Is diangle, complete diangle, that is 2 alpha is given 30 degree. So alpha will be half the conical diangle is 15 degree. Okay, draft is given, but I hope there is no need for that. So if we have the formula for the pipe drawing, what is first we have to calculate? Sigma D is equal to sigma y into bracket 1 plus b divided by b into bracket 1 minus the h final divided by h original to the power b, isn't it? So here actually sigma y is not given, so you can write like this: sigma d divided by sigma y in both the cases. So sigma y get cancels. So here is equal to 1 plus b by b into bracket 1 minus h final divided by h original to the power b. But for b, if we talk about the plug mandrel, isn't it? It is, we are taking as a stationary mandrel. Okay, so for stationary mandrel, b is equal to mu1 plus mu2 divided by tan alpha minus tan beta. But here no any thing is given for this beta, so it is what? 0, isn't it? That the mandrel angle. So for the plug we are talking about, we are not talking about the movable mandrel, please remember. So b will be how much? This mu1 plus mu2. As here mu2 also not given, then what we are assuming that this mu for mu1 and mu2 is 0.1, 0.1. Okay, we have to assume like that only, divided by tan of angle alpha. So what do you get for b? Mu1 is 0.1 plus mu2 is 0.1 divided by tan of 15 degree. So calculate this. So I hope you will get 0.747, isn't it? 0.747. Now go for calculation of this value, that is sigma d by sigma y. You will get it as 1 plus 0.747 divided by 0.747 into bracket 1 minus this h final is how much? 1.75 divided by 2.5 to the power 0.747, isn't it? So calculate what is the sigma d by sigma y value. So what is that? It will be around 0.547. This is for the stationary plug mandrel. Okay, the stationary plug. Okay, which is of course the cylindrical one, because beta value is 0. Okay, now you just keep this here, that is sigma d by sigma y for the plug, stationary plug is how much? 0.547. Now we will calculate it for the movable mandrel, and here no value of mu2 is given. Now I am writing for the movable mandrel, that is for movable mandrel. here mu1 is equal to mu2 is equal to 0.1, these are same, isn't it? So sigma d by sigma y kya banega, is equal to this b will be what, going to be 0. So which equation we are going to use for the movable mandrel? That is sigma d is equal to sigma y log of to the base 10, okay, it is 1 upon h original by h final minus, please remember this is log to the base 10 is there, okay, when mu1 is equal to mu2 is same for the movable mandrel because it is mu1, mu for movable mandrel it is mu1 minus mu2 divided by tan of alpha minus tan of beta. But please remember that movable mandrel generally कैसा होता है, straight cylindrical होता है, that's why this beta, this b value is going to be like 0 तो नहीं हो सकता, that's why we have this relation. So tell me what is sigma d by sigma y for movable? That is log to the base 10 into bracket 1 upon h original 2.5 divided by 1.75 minus 1. So कितना आएगा? If you calculate, it will be 0.368. 0.368. Okay, so you take the ratio of these two because final area will be the same. Okay, so the area final will be what? For force for the plug divided by force for the movable mandrel. You know how to calculate force for both of the conditions. Outer diameter is 50 mm, this thickness is going to change, so area for the final tube area will be same, so it is also not given in the complete manner, so only we can take the ratio of sigma d for plug divided by sigma d for movable. And again this same material, so the sigma y not to have the value, it will get cancel out, so you only need to write this sigma d for the plug is 0.547 divided by, for the movable mandrel it is 0.368, isn't it? So what is the answer? 0.547 divided by 0.547 divided by 0.368. So it will be 1.48. The ratio is equal to 1.48. So you can see there is a substantially decrease in the force when we are having the movable mandrel, isn't it? Okay. So this is one of the type. So see the question number 2 on this tube drawing operation. This is question number 2. In a tube drawing operation using a plug for the purpose, final dimension of the tube, outer diameter is 10 mm, inner diameter is 8 mm. If the drawing stress is 0.9 kN per millimeter square and the speed of drawing is 0.5 meter per second, they are asking what is the power rating of the motor. Okay, so you know that how to calculate the force is nothing but what, the drawing stress into the area at the end of the process, that is tube area, pi by 4 d outer square minus d inner square. So what is sigma d here? Drawing stress, it is 0.9 into 10 to the power 3 Newton per millimeter square into area. Final area will be pi by 4 d outer square 10 square minus 8 square. Okay, so calculate this. So if you calculate 100 minus 64 to pi divided by 4 into 0.9 e to the power, so it will be kilonewton. Okay, so this is the force, and what is the power? We know that power is equal to what? This force into velocity, isn't it? So force is how much? 25.45 into 10 to the power 3 into what is speed of drawing? 0.5. So what is the rating of the motor? It is 25.45 into 0.5. So it is 12.725 kilonewton meter per second. So it is nothing but the kilowatt, isn't it? So what is the rating of the motor? It is 12.725 kilowatt. So this is the kind of question we can have into the tube drawing operation. Thank you.